What we're going to introduce new in this lesson is oxygen is now going to bond onto some organic compounds. We're going to look at a couple of results here. So if we look at oxygen, it's in group 6, so it has 6 valence electrons, needs 2 to complete its octet. So that's why it's going to want to form 2 bonds, and it's going to want to form that in a couple of different ways. So first, they could do it with a single bond right here. Or it could also do it with a double bond right here. And we're going to focus on a couple of compounds today that have single oxygen bonds to them. The first one we're going to look at is called an alcohol. So the definition would be a compound that contains this OH hydroxyl functional group. So what we've got here is there's our functional group, OH, and then this R, what this R stands for is it stands for the carbon chain, and it depends, it could be 1, it could be 2, it could be 3, it could be 4, it could be 20 long. R just kind of stands for sort of in general that there's some kind of carbon chain here, and that's what this is saying. So R is equal to a alkyl group or a carbon chain. So get used to that. You're going to see R a lot of times in this part of our work. So they can be classified by the number of other carbon atoms that are bonded directly to the carbon atom attached to the hydroxyl group. So essentially we want to see how many carbon chains we have attached to the OH, and that'll tell us the degree of our alcohol. So for example here, we've got what's called a primary alcohol. So there's our OH, and then we have this one carbon chain here. So this would be defined as a primary alcohol. And there would be an example here. Again, you just have one carbon chain. So we go to the second one here, we've got 2 carbon chains. So here would be 1 carbon chain, and then this would be considered a different length of a carbon chain. So 2 carbon chains gives us a secondary one, and there's an example there. So again, you can see there's your first carbon chain, and then there's your second carbon chain. So 2 carbon chains attached to the OH makes it a secondary alcohol. And when we get to our third one, you guessed it, we have 3 chains, 1, 2, 3. And there's an example there. Again, you see 3 different chains. There's chain 1, there's chain 2, and there's chain 3. So let's look at naming alcohols. There's a couple of acceptable ways to do this. So you want to find the longest chain that contains the OH. And if it were like a propane, we'd take the E off the end and replace it with an OL. So you identify your longest chain. This one's only 1 carbon long, so it's going to have a meth. So methanol is the acceptable name. Take a look at this one. It's got 2 carbons. It's 2 carbons long. That's F, so this should be an ethanol. Now things get slightly more complicated when we get up to the 3-length carbon chain. We have a second rule coming here. So I want to use a number to indicate where the OH group is located on the parent chain, because it could be in the, I guess this would be the first spot, it could be in the second spot, it can't be in the third because that would be the first spot over here. So we need some kind of number. So there's a couple of different ways you can do this. So for this example, this OH group is on the first carbon, so you can put the 1 out front. It's a 1-propanol. However, there's a secondary method where you put the 1 inside the. So I've actually got the same one here. Now I've drawn it as a stick diagram. So it's in the 1 spot, so it's a 1-propanol. And now this time I've taken the 1 and put it inside here, so it is also a 1. If you're looking at this chain, this stick, and you might be confused, think of it like there's a carbon there, and a carbon there. So there are 3 carbons. That's where your prop is coming from. Now here's another one. The OH group is no longer on the first carbon. It's now moved to the second carbon. So this is going to be a 2-propanol or propatuol. Now what can also happen is you can also have some substituent groups as well hanging around here, and that's what rule 3 is about. So these two again are the exact same. So if you look at this one, we should have a chain of 3. So this is some kind of propane, and then this is in the 1 spot. So this is going to be some kind of propa-1-ol. And then it's a matter of numbering the chain. You want a number from closest to where the OH is. So that's the first carbon, that's the second carbon. It looks like we have a methyl group on the second carbon. So 2-methyl propa-1-enol. Or you can put the number not in the word, you can put it out front. Okay, so if you have multiple OH groups, then you're going to need a couple of numbers to show where they are, and even some prefixes. So here's some stick diagrams here. So we've got something that is 2 carbons long, and it's got 2 OH groups. So it is a 1,2 ethane. Now keep in mind, there's like the E has returned here. So the 1 and the 2 are referring to the OHs, and the F part is represented by that. Or ethane-1,2 diadol. Here's another one, and all we've really done is we've just added to the carbon chain. The carbon chain is now 3 long. So instead of it being an ethane, it's now a propane. So there you go, it's a 1,2-propane diol, or I put the numbers in between the words there. And this one here has got 3 OH groups, and so you're going to need a 1, 2, and a 3, and a tri to name this one properly. So 1, 2, 3, propane triol, or propane 1, 2, 3, triol. I included the slide just to show you some more examples here, some positional isomers, but again, it's just more examples to study from. And sometimes you can get some rings in here, and rings aren't that much harder. So you're going to identify the length of the ring and make it a cyclo, and instead of being like cyclopropane, you're going to make it into a cyclopropanol, changing the E to an O at the end. So here you go again, you count this one up. I think this one has 8 carbons if you count. So we're talking about a cyclooctanol. So cyclooctane has now become cyclooctanol. And here's another one with a couple of substituent groups. So this one has got 6 carbons in it, so it should be some kind of cyclohexanol because of the OH. So the cyclohexanol part is due to the OH here. And then notice this has been numbered 1, 2. So the 1,2 dimethyl goes right there. Now for some reactions. So there's a couple of simple ones we're going to look at this point. And the word hydration is key. What does hydration mean? Well, it means H2O, or more specifically, a molecule made of 1 H that's plus and 1 OH that's minus. And these are the things we're going to be using here in our reactions. So remember this H and this OH when we do the reaction. So here's the first one. We're taking some kind of alkene here, and we're reacting it with water, which is HOH. So all that's going to happen here is this double bond is going to disappear in a sec. It's going to go, and then we're going to be able to put a hydrogen there and an OH there, or kind of vice versa. So the double bond is broken. I guess this is just flipped around, but it's still the same thing, and we still have an alcohol here. So we're still looking at, again, naming this one, it's 4 long, so it's a butanol. OH is in the 2 spots, so 2-butanol. We also have a methyl, 2-methyl-2-butanol. Couple more examples here. Now this is the opposite. This is the dehydration. So we're going to make water as a product. So if we're looking at the first example here, really we're going to be removing those 2 and then changing that to a double bond, like so. And then on this example here, it looks like we're going to remove these 2 and change that into a double bond, like that. And then you can go ahead and name those ones as well. Ethers. So also a single bonded oxygen, and really what's happening here is we've got an oxygen in between of 2 carbon chains. They could be the same length, or they don't have to be the same length. And that's what this little prime by the R stands for. It says, well, it could be the same as this R, but it might be different, so we'll put this little prime. So let's look at some examples here, and the names are included too. So the first one we have is a diethyl ether. So looking at this one, you identify it as an ether because the oxygen's in the middle. And then you say, okay, there's my carbon chains, and they're each the same length. So the di is standing for the fact that they are both the same length. So diethyl ether. This one's a little more complicated. It's got what we call an isopropyl group. This is made of 3 carbons, and they're not in a chain. They're more of like in a, I don't know, they're just sort of bent up. And it's connecting to the middle of the chain. That's where the iso thing comes from. And then we also have the ethyl here. Now you notice for this one that we've included our alphabetical order. So ethyl is coming before propyl. So the ethyl part comes before the propyl part. And then because of the oxygen, you had the ether in there too. So ethyl isopropyl ether. You could even say we took that out and just bonded that there. Then it would just be ethyl propyl ether. And here's one more example here. So there's our oxygen in the middle, making it an ether. We've got a methyl group, so alphabetically it will come first, and then we have a propyl group there, and it will come second. So methyl propyl ether. They should be easy to spot. There is a second way of naming these ones though. And so there we've got some IUPAC, just stands for the naming convention. So you want to look for your longest continuous carbon chain, and that's going to be your parent name. So we're actually going to use a parent name. We're not going to use the word ether anymore. We're going to end with like propane, methane, something like that. And then the other chain is we're going to change to OL, and we're going to have the word oxy in there. So methyl turns to methoxy, and the oxy tells you that it's an ether. The two words don't seem that connected, but again, you have to remember it's just oxygen here. So here's a first example. We've got 1-ethoxybutane. So the butane is coming from the fact that this chain here is our longest one, and it's got 4. So that is our butane. And then we've got the ethyl group, so ethoxy, and there is a number included in this one. And here's the same thing. So we've got, there's our methyl group, and there is our propyl group. So there's the propyl. That's going to be the propane is going to be the ending right there, all in red. And then we also have that methyl group, which is named right there. And then we've got this one thing standing right there. Personally, I prefer the other method, but this one is valid. And there's one more example, 2. So 2-methoxy. Now sometimes you can combine them both. And if that happens, the alcohol is going to take precedent over the ether. So we have a 4-methoxy 2-butanol. So your longest chain will be your butanol. And then you've got the meth part there. Now the 2 is telling me where that OH is located, and the 4 is telling me where the rest is located. So it should be off the 4 carbons over there.